So what else can we do with the Gauss-Jordan algorithm? Well, we can apply the Gauss-Jordan algorithm to augmented matrices. And keep in mind, every step of the Gauss-Jordan algorithm is a row reduction. And if you think about it, in an augmented matrix, each row represents an equation. And when we do row operations on those rows, what we're really doing is equation arithmetic. So let's look at an example here. Here we're looking at an augmented matrix with two rows, and we have two variables here followed by the augmented column. So this is a system with two equations and two variables. Well, let's start applying the Gauss-Jordan algorithm. In my 1, 1 position, I have a 1. That'll be my pivot. But I don't have a pivot column, so I should clear out the 3 below it. So I can do this with row addition, according to the algorithm. So I take row 2 and I subtract 3 row 1. That zeroes out my entry below my first pivot. And so that first pivot column is now legit. Now I move to the 2, 2 position. This is not a pivot yet because it's not equal to 1. I can turn it into a 1 by scaling the second row here by -1/2. When I scale by -1/2, I produce a 1 in the 2, 2 position. So that's now my second pivot. And I can make this a pivot column by looking at the 2 right above my pivot and eliminating it using row addition. The row addition here would be row 1 minus 2 times row 2. That produces a 0 above my second pivot position. And now I'm in reduced row echelon form. Well, if we look at the reduced row echelon form here, we can do our analysis given by the Roach-Capelli theorem. We have a consistent system because there's no pivot in the augmented column. The number of solutions is exactly equal to 1 because there are no free variables. And if we look at these two equations, the two equations are saying x equals -6 and y equals -9/2. So we know that we have a unique solution given by -6, -9/2. So this is the power of the Gauss-Jordan algorithm. It takes a system that starts off as something ugly, where it's completely non-obvious what the solutions are, and it turns it into something that's much nicer. And by much nicer, I mean reduced row echelon form, where we know exactly how to analyze the system. And luckily for us, we have a taxonomy given by the Roach-Capelli theorem. If we want to study any system, A augmented with B, well, all we really need to do is take the reduced row echelon form according to the Gauss-Jordan algorithm, and then study the reduced version of the system. So the Roach-Capelli theorem tells us that every system falls into one of the following 3 categories. Either the system is inconsistent with no solutions, and what this means is that in the reduced row echelon form of the system, we have a pivot in the augmented column. The way we test for this numerically would be to compare the rank of the coefficient matrix A to the rank of the augmented matrix. If the rank of the coefficient matrix is less than the rank of the augmented matrix, that means that I added a pivot when I augmented, which means that I'm inconsistent. The other 2 categories are the consistent categories. Consistency means that the rank of the coefficient matrix equals the rank of the augmented matrix. Because for consistency, adding on the augmentation should not change the rank because I won't be adding a pivot. But there's 2 categories of consistency. Either we're consistent with one solution, meaning that in the reduced row echelon form, we do not have free variables, meaning that the nullity of the coefficient matrix is 0. Or we're consistent with infinitely many solutions, meaning that we have free variables in the reduced form, and consequently the nullity is greater than 0. So the major takeaway here is that if we want to study A augmented with B as a system, all we need to do is study the reduced row echelon form of that augmented matrix, and then do the analysis as we previously studied. The reason we can do this is in the last statement here. The system represented by A augmented with B has the same solutions as the system given by the reduced row echelon form. So let's do a few examples. So here I was studying this system, which had three equations with four variables. And as you can see, this system is terrible. So how did I make my life easier? I took this augmented matrix and I plugged it into the Gauss-Jordan algorithm. And then the Gauss-Jordan algorithm spit out a reduced row echelon form version of the system. I know how to do the analysis here. In the reduced row echelon form, it looks like I have a pivot in the x1 column, a pivot in the x2 column, but evidently I have a pivot in the last column as well. Here we can sort of see that in the reduced row echelon form system, the last equation is 0 equals 1. So we know that the system has no solutions. This is an inconsistent system, and we'll never find a solution no matter how hard we try, because there is no solution. This is not so easy to see in the original system, because the original system has all of this noise in it. The Gauss-Jordan algorithm strips the noise out and allows us to see clearly what's going on. Here's another example. Here, this example has four equations with four variables. And again, this one's terrible. There's all these ugly numbers here. Well, I plugged this system into the Gauss-Jordan algorithm, and the Gauss-Jordan algorithm spit out the reduced row echelon form of this system. I could do the analysis here. It looks like I only have three pivots, and none of these three pivots is in the augmented column. So this system is consistent. What are the variable types? Well, x1, x2, and x4 are in the pivot columns, so those are my dependent variables. x3 is the only other variable. That's my free variable. And how do I solve the system now? Well, so remember here, the nullity here of the coefficient matrix is greater than 0. It's equal to 1 because we have one free variable. That tells us that we'll have infinitely many solutions. So how do we go about finding these infinitely many solutions? Well, remember our procedure says, replace the free variable with a new variable. So let's call that C1. So I'm replacing x3 with C1. And then we're using the equations in the system to write the dependent variables in terms of the free variable. If you look at the very first equation of the system, it's x1 plus 3x3 equals 5. And since x3 is C1 now, we can solve for x1 and we get x1 is 5 minus 3c1. If we look at the second equation of the system, that is x2 minus 4x3 equals 7. But we're setting x3 equal to c1. And if we solve for x2, we get 7 plus 4c1. Finally, what is the third equation here in the reduced row echelon form? The third equation is demanding that the fourth variable x4 equals -9. So we have to put that in the solution vector. So now we have the full solution vector, and I always separate this out as the particular solution plus the linear combination of the other vectors that are organizing the coefficients in front of my free variables. In this case, the coefficients not attached to C1 are 5, 7, 0, and -9. And the coefficients in front of C1 are -3, 4, 1, 0. So here we see where all the infinitely many solutions are coming from. You can start with the solution 5, 7, 0, -9, and then add any scalar multiple you want of -3, 4, 1, 0, and you get a new solution to the system. Let's do one more example here. So here we have a giant, totally gross system. How many equations do we have? We have 1, 2, 3, 4, 5. We have 6 equations with 5 variables. So this system is terrible. So how do we make it better? We take the system, we put it into the Gauss-Jordan algorithm, and we study its reduced row echelon form. The reduced row echelon form here is quite nice. You can see that we have 1, 2, 3, 4. We have 5 pivots, and they're all to the left of the augmentation. So this system is consistent. And moreover, since we have 5 pivots with 5 variables, we don't have any free variables. The nullity of this coefficient matrix is 0, meaning there are 0 free variables, which means we'll have only one solution. And we can figure that solution out by looking at the equations. The first equation is just x1 equals 7. The second equation is x2 equals -6. then x3 equals 4, x4 equals 9, and x5 equals negative 1. So there's only one solution to this system, and it's given by x1 equals 7, x2 equals negative 6, x3 equals 4, x4 equals 9, and x5 equals negative 1. So clearly here, the Gauss-Jordan algorithm helped us take something completely terrible and reduce it to something very nice that we can study.